Welcome to the hidden world of atomic physics. Everything around us appears solid and unchanging, but deep within the heart of matter, a dynamic process is unfolding. We are exploring radioactive decay and half-life. This is the story of exploring nuclear transformation, a fundamental force of nature that shapes everything from the energy of the stars to the medical treatments that save lives. Today, we will visualize the invisible forces that govern the stability of the universe itself. To understand this phenomenon, we must first answer the question, what is radioactivity? At its core, it is a spontaneous nuclear transformation. It is the process where unstable nuclei emit radiation in a desperate bid to achieve stability. This groundbreaking concept wasn't always known. It was discovered by Henri Becquerel. His accidental yet groundbreaking finding in 1896 changed the course of science forever, revealing that atoms are not the indivisible building blocks we once thought they were. Not all atoms are created equal. We must look at isotopes and stability. On one hand, we have stable isotopes, where a strong nuclear force maintains tight nucleus binding, keeping the atoms secure for eternity. On the other hand, there are unstable radioactive isotopes. In these rebels of the atomic world, an unfavorable proton-to-neutron ratio causes decay. The nucleus is literally tearing itself apart to find a more balanced state. Inside the nucleus, a titanic tug-of-war is taking place. We call this the force of stability. The hero here is the strong nuclear force, which binds protons and neutrons together, but it fights against electromagnetic repulsion. This force pushes positively charged protons apart, trying to explode the nucleus from the inside. When the repulsion starts to win against the binding force, radioactivity is the inevitable result. So how does a nucleus save itself? The first method is type 1 alpha decay. In this dramatic ejection, the nucleus emits a helium nucleus, which consists of exactly 2 protons and 2 neutrons. This is a massive loss for an atom. Consequently, the mass decreases by 4, and the atomic number decreases by 2. It is a fundamental transformation of one element into a completely different one. The second method is subtler, but equally transformative. Type 2 beta decay. Here, a neutron converts to a proton, and in the process, it releases an electron. This electron is ejected at high speed. The result? The atomic number increases by 1 because we have gained a proton, but the mass remains unchanged. It is a brilliant example of nature's alchemy, turning neutrons into protons to stabilize the core. Sometimes the nucleus doesn't need to lose particles, but just pure energy. This is type 3 gamma emission. This involves the release of high-energy electromagnetic radiation. It is essentially a photon emission from an excited nucleus. Crucially, there is no change in atomic structure. No protons or neutrons are lost. Only energy is released as the nucleus stabilizes itself from an excited state. These different types of radiation interact with the world in very different ways, defined by their penetration power. Alpha particles have the lowest penetration. They are massive and can be stopped by paper or skin. Beta particles have moderate penetration, requiring a barrier like aluminium foil or clothing to be stopped. Gamma rays, however, possess the highest penetration. To stop them requires thick lead or concrete shielding. While decay is random for a single atom, it is incredibly predictable for a large group. This brings us to defining half-life of T1/2. This is defined as the time for half the nuclei to decay. It is a constant characteristic value for each radioisotope. Most amazingly, it is independent of external factors. Whether you freeze it, heat it, or crush it, temperature and pressure have no effect on this internal atomic clock. If we graph this process, we see the decay curve, also known as exponential decay. Let's trace it. At the start, we have 100%. After one half-life, exactly 50% remains. Wait another half-life, and we are down to 2 half-lives where 25% remains. By 3 half-lives, only 12.5% remains. The substance never truly disappears, but it vanishes towards zero in a beautiful mathematical curve. Let's apply this to a real-world scenario with half-life calculation example 1. Imagine we have a starting amount of 100 grams of iodine-131. The half-life of iodine-131 is 8 days. If we wait for 8 days, which represents one half-life, what happens? We look at the remaining amount and find exactly 50 grams. Exactly half of the original mass has transformed. Now let's extend that timeline in half-life calculation example 2. We started with 100 grams. After 8 days, we have 50 grams. Wait another 8 days, totaling 16 days, and we drop from 50 grams to 25 grams. Extend that to 24 days, and we are down to 12.5 grams. Finally, after 32 days, or 4 half-lives, we are left with just 6.25 grams. The predictable nature of this decay allows us to calculate remaining amounts with precision. For those who speak the language of mathematics, this relationship is described by the half-life equation. The formula is written as n of t equals n0 times 1/2 to the t power of half. Here, nt represents the remaining amount or quantity at time t. N0 is the initial amount or starting quantity. Finally, t represents the time elapsed, the duration of decay. This single equation allows scientists to predict the future or reconstruct the past. One of the most famous applications of this science is radiometric dating, specifically using carbon-14. This technique is used for dating organic material. It works because carbon-14 decays after an organism dies. With a half-life of 5,730 years, it acts as a stopwatch that starts ticking at the moment of death. This method effectively measures samples up to 50,000 years old, allowing us to date ancient artifacts and fossils. But what about things older than 50,000 years? For that, we use dating rock formations with uranium-238 dating. This isotope has a staggering half-life of 4.5 billion years, making it perfect for ancient rocks. By measuring the parent-to-daughter isotope ratio, specifically the ratio of uranium to lead, science determines Earth's age. The oldest rock will always have a higher daughter isotope ratio compared to recent sediments. Radioactivity isn't just for dating rocks. It is a vital tool in modern healthcare. In the field of application nuclear medicine, we use tracers. A prime example is technetium-99m, a medical tracer with a very short half-life. Doctors inject this into the body, where its emitted gamma rays enable organ function imaging. It allows us to see inside the human body without a single incision. Perhaps the most impactful application is nuclear power. This relies on the nuclear fission process. Inside a reactor, we split uranium-235 nuclei. This initiates a controlled chain reaction that maintains energy release. This massive release of heat is used to boil water, which drives turbines and generates electricity. It is the process of turning atomic instability into the power that lights our cities. With great power comes great responsibility. We must strictly adhere to safety and shielding requirements. The golden rule of radiation safety is the ALARA principle, which stands for keeping exposure as low as reasonably achievable. This involves time, distance, and shielding. We use material-specific shielding, simple paper for alpha particles, but thick lead for gamma radiation. Safety is engineered into every step. We take these precautions because of the biological effects of radiation. Specifically, ionizing radiation damages tissues. On a cellular level, it causes DNA mutations, increases cancer risk, and leads to cell death. We classify the danger into acute versus chronic exposure. High doses can cause immediate radiation sickness, while lower, long-term doses increase long-term cancer risk. In summary, radioactivity is a story of transformation over time. It is driven by unstable nuclei seeking stability. We have learned that radioactive decay is a fundamental transformation of matter. We understand that half-life provides a predictable rate of exponential decay with constant timing. From dating ancient history to advancing medicine and generating energy, these are the essential principles for modern science.